We learned that linear models can be used to model a variety of data, and they're relatively easy to fit in R. Now, applying transformations to data that might not fit our normality assumptions, that's going to give us even more modeling flexibility. But what about data that still doesn't conform to normality, even after a transformation? Well, tree fitting is one possibility. As we saw in the last lecture, regression trees and classification trees, they allow us to fit models to nonlinear data. But even those methods aren't effective on data that doesn't have natural splits, whether vertical or horizontal. Now, what can we do when we have data for which transformations and tree algorithms aren't effective? Well, one idea is called polynomial regression. Polynomial regression lets us extend the linear model by adding powers of predictors to our model. So this gives us a really clean way to fit nonlinear data or nonlinear models to our data. All right, remember the standard linear regression model? Here we could model y as beta naught, so that's our intercept term, plus beta 1x1, plus beta 2x2, and so on, plus e sub t, where those betas were our coefficients, and e sub t was a zero mean normal distribution error term. Now, instead of predictors x1, x2, and x3, we now have a polynomial function with predictor x, where y is modeled as follows. Y equals beta naught plus beta 1x plus beta 2x squared plus beta 3x cubed, and so on, plus our error term. This is known as polynomial regression. All right, let's look at an example in R. Now we're going to look at a data set called the Boston data set. And it's got a lot of variables, but we're going to restrict our attention to two of those variables. In fact, the last two. So you need the mass function, which is where that data set is located. Now, initially, would you think that maybe average house prices for neighborhoods would be related to socioeconomic status? In fact, I would imagine that as house prices increase, status in the population would probably decrease, right? If I have a lower socioeconomic status, I probably can't afford a more expensive house. So those are the two responses that we're going to think of. So we're going to use the median house value for select neighborhoods in Boston, which is MED-V. We're going to use that and see if we can explain it by socioeconomic status of the population. And this is by percentage. That's our LSAT variable. All right, so intuitively, we think there might be a linear relationship. And so our first step is actually to fit a linear model to look at that. All right, we've done this before in simple linear regression. We're just going to use the LM command. So fit a linear model to the median house value, and our explanatory variable is lower status in the population from our Boston data set. So we can graphically look at this output to see if a linear model gives us a good fit. All right, here's the summary function. So you see our call where we fitted the median house price on lower status. Notice our residuals. So they range from -15 to a maximum of 24 with an average of -1.3. And then you see the coefficients in our model. So notice, actually our coefficients are significant. And our R-squared value, 0.54. So just looking at the regression output, you might think that a linear model is actually a good fit, right? There's a significant coefficient for our intercept term and for our lower socioeconomic variable. But look at the actual fit of our data. Notice here there's actually a curved linear relationship between status and median home values. And here, as we try to fit just a line of this data, you can kind of start to see that we're not really capturing all of the curvature in those values. So maybe this line isn't the best representation of the fit between status and median home values. Well, in this case, when you've got data that has this type of relationship, a polynomial regression is going to give us flexibility to fit a nonlinear curve to that data. Let's do that now. So now we're going to do a regression of our median house price onto a quadratic polynomial. So we're going to take our lower socioeconomic variable, but we're also going to square it, right? So median house price modeled as a function of LSTAT plus LSTAT squared. And notice we have to use this I, which is our indicator function, so that it actually takes the square of that variable. Notice here, the polynomial fit seems to do a better job of actually calculating the trends in your data. In fact, look at that R squared value. It's actually improved. Notice here that once we fit a polynomial regression, we've improved our adjusted R squared value from around 0.54 up to close to 0.64. And each of our coefficients are all significant. Now, you'll notice we had to use that indicator function, I, of LSTAT squared, to square the variable. But that's not really intuitive. In fact, what happens if we just forget that? If we just put in LSTAT squared, what does R do if we leave off the indicator? Well, here we've now modeled median house price on LSTAT and just LSTAT squared without the indicator function. Notice what R does. It just fits the same model as median value on lower status. In fact, LSTAT squared looks like a variable name that we forgot to define, so it gets ignored without having that indicator function. So the indicator function is necessary when we want to fit polynomial regression models. Notice here, we can also do a second degree fit. The quadratic model fits the data pretty well. In fact, better than our linear one did. But notice that it has pretty poor behavior for low socioeconomic status percentage above 25%. In fact, the data doesn't seem to support the curve where it turns upward. We wouldn't expect home values to increase as the percentage of low socioeconomic status increases above 25%. So in this case, a higher order model might give us a better fit. We can actually extend the polynomial out to 3 degrees and get an even more accurate fit of our data. Here's how we do that in R. We're going to use the LM function for the median value of our home, and we're going to regress that on low socioeconomic status percentage plus that variable squared plus that variable cubed from our Boston data. Let's look at a summary of that output. Notice here, each of our variables is significant. You've got p-values that are way below 0.05, even below 0.01. So how does this actually look on our data? Well, let's look at that too. Oh, but let me draw your attention to the R squared value. Notice that our R squared increases from the quadratic fit. We go from 0.6393 to 0.6558 when going from our second degree to the third degree polynomial. Now, it better models the tail end of our data, suggesting that home values would continue to decrease as low socioeconomic status increased. Now, why stop at a third degree? I mean, in fact, we could fit a fourth degree model. Here's how we do that in R. Notice here, in our fourth degree polynomial, which seems to do a better job of fitting the data less than 30% of our lower socioeconomic range. But look what happens when our low socioeconomic percentage goes above 30%. So we need to think about what this is saying because this model is suggesting some questionable behavior. I mean, there's again no reason to believe that home values would increase as the percentage of low socioeconomic status also increased, which is what this fit is telling us. Now, we could continue with a fifth degree fit. In fact, the more we fit the data, when we increase the polynomials, we actually more fine-tune our fit to the data. So let's see what that looks like now. Notice here, the fifth degree polynomial is really capturing the shape of the data. And notice that behavior in the tail end. Well, it's tending to turn down, which is what we might expect it to do. All right, you might be asking, why stop at fifth degree when you could go to the 15th degree? I mean, why not? Let's just see what happens if we ramp up to the 15th degree polynomial fit of our data. Now, here's the code to do that in R, and here's the output. Okay, notice here, when we go up to 15 polynomials, we're getting a pretty accurate fit of our data. Actually, the model is curving, it's really capturing not only sort of the linear trend, but also some of the curved linear. But look what happens in the tails. We really start to try to match those values too closely. In fact, our model becomes overfit. So an overfit model is basically one that's too complicated to convey useful information about your data set. In other words, the model becomes tailored to fit the nuances in our specific sample rather than reflecting the overall population. So if we were to draw another sample, it would have its own nuances. And our original model, well, it probably wouldn't fit that data very well. So instead, we want our model to approximate the true model for the entire population. Our model shouldn't just fit the current sample, but new samples too. Now, the fitted line for a 15 degree polynomial illustrates the danger of overfitting models. I mean, this model appears to explain a lot of the variation in our response, but the model is really too complex for our sample data. Now, generally, it's unusual to use polynomial models greater than maybe 3 or 4 degrees, because after that, we risk overfitting. But we also risk generating too much variance. So one solution is to try step functions. All right, polynomial functions let us model the behavior of nonlinear structure in our data with a global model, right? It's put on the entire data set. What if we have reasons not to fit a single global model? Well, another approach is to use a smaller, more local model. So this is going to capture that nonlinear trend in the data, but on a local level. Imagine we break our data into a certain number of bins, say K bins. And each of those, we're going to fit a constant in each bin. So essentially what we're doing is we're going to create the bins by selecting K cut points in the range of our data variable X. And then we're going to construct K plus 1 new variables. These are going to behave kind of like dummy variables. So they'd only take on a value of, say, 0 or 1. Let's look at an example. So back to our Boston data. Let's look at a 5-year step pattern for that data. So here's what a step function would look like if we were to fit it on our Boston data. Notice here, we've specified the cut, and we've set breaks equal to minus infinity to 5, 10, 15, and 20 years, and then out to plus infinity. So ggplot is going to give us this plot along with the steps functions. Here's our data. All right, notice for this particular data set, our Boston data set, a step function's actually not a bad idea because it really kind of captures the movement of our data over time. Now, we could change our number of bins, we could change those years to sort of better fit our step function, but we do a really great job. The only drawback might be in the tail. So when our lower socioeconomic status increases, we don't really have any more steps to move around to capture that. Okay, so when you're comparing, say, a third-degree polynomial with a step function, how are you going to decide which one is better fit? Well, a couple of things we can do, which we already know about. First, the r-squared value. We can look at our r-squared for each of those and see which one is higher. But we could also analyze the residuals. So they're going to be residuals from both polynomial fit and the step function. So we can check those for normality, for linearity, and that could also help us decide which one is better. Let's do another example in R. Here we've got a data frame called onions, and it has 84 sets of observations from an experiment involving the production of white Spanish onions in 2 South Australian locations. Let's focus on 2 of those variables. Here we're going to look at density and yield. Now, density is the areal density of the plants, so the plants per square meter. And yield tells us the onion yield in number of grams per plants. So we would expect that maybe as our density, say, increased, if we put more plants per square meter, well, our yield might either increase or it might decrease if they're sort of too clustered together. So I'm not really clear how this relationship might look, and my first thought might be to see if there's a linear fit to them. All right, here's our data. Yield versus density. Notice here, as our density increases, so we start to put more and more plants together, the yield is actually decreasing. Right? So those plants don't really have enough room to produce onions. But look at our linear fit. Again, we're not quite capturing the trend in that relationship. So what might we do? Polynomial regression comes to the rescue. Here's a second-degree fit. Again, nice pattern. So now we're better capturing the curvature, but you always want to check out what's happening in the tails. Notice that that second-degree fit is starting to curve upwards, meaning that, well, if we just keep increasing density past some point, the yield is going to start to come back, and that's probably not true. So this wouldn't be a good fit for our data. All right, let's check out a third-degree fit. Notice here, the third-degree polynomial fit is curving in a way that we might expect, right? So as density continues to increase, we're going to expect that yield to really go to 0, right? You can only get so many in a square meter before nothing's really going to grow because it doesn't have space or nutrients. So this model sort of fits our intuitive explanation. Here's a fourth-degree fit, which kind of has the same problems of our second degree. Notice it starts to flatten out and even slightly curve at the tail end. So now I want to turn your attention to yet another class of cases where we might want to fit a model to nonlinear data. Now, often across all of STEM, we face the problem of modeling binary data. In fact, we might want to predict whether our patients will live or die, or species will thrive or go extinct, or maybe will a building fail or stay standing. If I'm in it, I hope it's going to stay standing. We might also want to predict whether a patient will accept or reject an organ transfer. So in this case, the problem is that we're dealing with binary outcomes. Well, one solution would be we could just code, say, alive as 1 and dead as 0, and then we could fit a line through those points, just as we would with the linear regression. Well, that's possible. In fact, we could then try to interpret those values of the fitted line as the probability of survival. But the trouble is, we're dealing with a probability. And regression can easily give us illegal values that are less than 0 and greater than 1. So we'd want to do a regression, but we've got to restrict it to values between 0 and 1 so that we get a correct probability. Also, linear models, they don't handle probabilities well. Right? Smoking 2 cigarettes per day might double my risk of cancer compared to, say, 1 per day. But increasing from 11 to 12 per day, might not make such a big difference. And once we predict that a patient has a 100% chance of an outcome, we're maxed out. There's no new information about that patient that could actually improve their odds. So another way of thinking about how to model probabilities is to transform them. And we can do that using what we call the odds function. The odds is defined as our probability P over 1 minus P. So this is the probability of something happening divided by the probability of it not happening. Now, odds are commonly used in gambling, right? Especially with horse racing. There's a 9 to 1 against, right? That means we have a probability of 0.1. Or if there's even odds, that's a probability of 0.5. Or 3 to 1 on, probability of 0.75. So we may have heard this terminology used quite frequently. Well, we're now going to apply it to statistical models. So the odds gives us a value that ranges from nearly 0 for very small probabilities to positive infinity for probabilities that are essentially at 1. But with one more transformation, we can get a value that's unbounded over the entire real numbers. And this is called a logistic function. Y equals the log of P over 1 minus P. All right, probabilities get transformed through the logistic function, and we call those logit values. So now we've got a value that ranges from minus infinity to positive infinity. Linear regression is going to love this because now I can fit a model to this data. So logistic regression is a regression model in which the response variable, our dependent variable, has a categorical variable, such as true, false, 0, 1, dead or alive. And so it deals with measuring the probability of a binary response. So in R, we're going to use the function GLM, and that's going to create a logistic regression for us. Now, logistic regression is a generalized linear model. That's where that GLM comes from. And we use that to model the binary categorical variable with both numerical and categorical predictors. Now we're going to assume a binomial distribution produce the outcome variable. And so we therefore want to model that probability, that P, of success for a given set of predictors. Now, in order to specify our logistic model, we need to specify what we call a link function. The link function is a function that relates the mean of the response to the linear predictors in the model. Right? We've got to sort of link our response to our predictors in a special way. And that's what we get from a link function. In our case, there's a ton of options, but the most commonly used one is the logit function. And is similar to the probit function, which is based on the normal distribution. Here, the logit of P is again the log of P over 1 minus P, where that probability is going to range from 0 to 1. Now notice what the logit function is doing is taking a value between 0 and 1 and is mapping it over to a value between minus infinity to infinity. So the general mathematical equation for a logistic regression is going to be our logit function, so log of P over 1 minus P, and then we just model that as beta naught plus beta 1 x1 plus beta 2 x2 on out to our residuals, E sub t. Let's look at an example. We've got a cool data set in R called MT cars, and it describes the different models of a car with their various engine specifications. So in the MT cars data set, the type of vehicle transmission, whether it's automatic or manual, is described in the outcome AM. And this is a binary variable. It's either 0 or 1. So suppose we wanted to model whether or not we had a manual car or an automatic car. This is a prime example of when we would use a logistic regression, Because remember, this binary categorical variable, this is our y variable. This is what we want to learn about from our predictors x. All right, so we're going to use logistic regression to model the relationship between the columns, AM, and those other three columns. In this case, we're going to use horsepower, HP, weight, which is the weight of the car in 1,000 pounds, and cylinders, or CYL, which gives us the number of cylinders in the car. Here's our data. Now, in R, we're going to use the GLM function, and that's going to create the regression model that we need, and it gives us a summary for our analysis. Now, we're going to fit that the same way we do a linear model, except instead of LM, we're going to use GLM. So the only thing we've added is a G. We also, though, have to specify the type of GLM that we want to fit, and we do that in the family argument. Notice here, here's our GLM fit. Same formula that we do for a linear regression, right? We're modeling AM, automatic or manual, on the cylinders plus the horsepower plus the weight from our empty cars data set. But we need to specify that we're modeling it using the binomial family. So we're assuming that AM is from a binomial distribution. All right, here's a summary of our fit. Now, notice this is similar to linear regression output. Logistic regression gives us estimates for the coefficients. So here you see we have an estimate of around 0.48 for cylinders and 0.03 for horsepower. It also gives us the standard error. Now notice your standard error for cylinders, 1.07, is actually more than twice the estimated value. This is sometimes a clue that indicates that that estimate is not going to be significant. We also see the associated z value. So this is our z test statistic that tests whether our coefficients are individually significant. And the last column is the p-value. Remember, p-values that are less than 0.05 indicate that our coefficient is statistically significant. Now, since the p-value in the last column is more than 0.05 for cylinder and horsepower, we consider them to be insignificant when they contribute to the variable transmission, or AM. So we'd want to take them out of the model. In fact, only the weight variable impacts AM in this logistic regression model. So let's remove those other insignificant terms and rerun our model. Here's our code in R. I'm going to call that glm.fit2 because this is our second time running it. And notice now my formula has changed. I'm only measuring AM, which is automatic or manual transmission, as a function of weight. Again, from the empty cars data set from the binomial family. And that binomial assumption goes to the variable AM. All right, here's our output. Notice our estimate for weight actually changed from around -9 to -4. And the p-value decreased. So that means weight became even more significant. It went from 0.027 to now 0.005. Here's code that we can use to look at our model graphically. Right? So now we're plotting empty cars weight versus empty cars AM. And so from that, we're going to add G. That's our general linear model fit. And we're going to assign Y weight to the predicted model fit and then add lines to that. It's kind of a complicated code, but it gives you an amazing output. Check this out. So remember, our automatic or manual is binary, so it's 0 or 1. And our logistic regression is trying to fit a continuous function to that data, right? It goes from -infinity to infinity. So here you see weight on the x-axis in 1,000 pounds versus AM on the y-axis. You can see for lower weight values, say up to around 3,000 pounds, those cars tend to be manual transmissions. Whereas, as the weight of the car increases, we tend to see more automatic transmissions. This green line is the fit from our logistic regression. So it's capturing how that probability is changing as the weight changes. Now here's our model, right? How would we actually get from this logit score back to the probability? Because remember, we modeled y as log of p over 1 minus p to get us into that continuous space. Here's how we do it. So now our model is log of p over 1 minus p. And that's going to equal our y-intercept term, which is 12.040, minus our parameter estimate for weight, which was 4.024, times the variable weight. All right, so we need to work our way back through that logit score construction process. So here's where we start. And let's calculate the probability of having a manual transmission when the car weighs 4,000 pounds. So in this case, we would just plug in a weight of 4,000, but we want to solve for that p, that probability. Well, if I want to get rid of the log, one way to do that is to take the exponential of both sides. So I take the exponential of my log p over 1 minus p, which gets rid of that log. So now I'm just left with p over 1 minus p is equal to the exponential of the right side of my equation, 12.04 minus 4.024 times 4. This reduces to just the exponential of minus 4.056. So now I need to solve for that p. So p over 1 minus p is equal to 0.0173. And if I solve for it, I get 0.0173 over 1.0173 to give me a probability of 0.017. So my model is going to say that a car that weighs 4,000 pounds has a 1.7% chance of being a manual transmission. And this is actually what we kind of saw in the data. Let's do another one. What's the probability of having a manual transmission when your car weighs 2,000 pounds? So this is to the left of our scatter plot. We can calculate it directly from our logistic regression model. Again, plug in 2,000, take the exponential of both sides, and then solve for p. P over 1 minus p is equal to 54.16. And here I get a p of 0.98. So the model says that a car that weighs 2,000 pounds has a 98% chance of being a manual transmission. Now, polynomial and logistic regression are not without their pitfalls. In fact, if we try to extrapolate from fitted polynomials, that was a no-no. You saw in some of your examples where you noticed that there were confidence bands that started to get bigger. Yeah, that's telling you that it's pretty dangerous when we do that. So in higher order polynomials, it's a great fit to the data that you have at hand, but often it can overfit the data. But predictions and extrapolations for values of x that go outside of that range, they're going to be often incorrect and sometimes even invalid. So make sure you don't do that.